I'm a recent graduate from UC Berkeley, where I studied with John Hulsenbeck. And I'm going to be sharing some research on how we can use biogeographic processes to help estimate phylogenetic parameters. And the types of phylogenies I'm most interested in here, like many evolutionary biologists, are dated trees. Why are dated trees interesting? Well, in order to understand the broad context of an evolutionary event, typically you want to know the timing of that event. And for that, most often dated trees are used. For example, did species diversify rapidly when faced with climate change? Those are questions where you need to calibrate the timing of the event to some geological event. Now the problem is that when we infer phylogenies, typically it's using molecular data. And the models we use for those estimations will rely on the constant rate substitution process. The problem here is that you can't use this process to separately identify rate and time parameters. How these branch lengths are estimated is in the expected number of evolutionary events. And this is the product of the rate at which events occur and the amount of time that evolution has been in process. So for example, if we expect for there to be 10 events, it could be that the events occurred at rate 1 for 10 units of time, or it could be that you expect the rate to be 10, or that it could be that the rate is 10 and evolve for 1 unit of time. Fortunately, when fossils are available, you can use fossil calibration methods to essentially solve for the time component of phylogeny. And this is done essentially by conditioning on the ages of the fossil, treating the data that you input into the model as the joint distribution of traits over the fossil taxa and the extant taxa that are in your phylogenetic analysis, and then using a morphological clock to institute that basis of time. But as you can imagine, if you don't have any fossils, you're in a little bit of trouble. And this is actually the case for most groups of organisms. If you're not working on turtles, for example, you may have no hope of fossils. But these piles of sand are your fossils reduced to rubble. So when you don't have fossils, what are you going to do? The methods we have are very limited. For instance, you might use some type of empirical estimation for the substitution rate to solve for the rate parameter. But and the other method that's often used is using biogeographic calibrations. The work that I'm going to be talking about is how we can, instead of using prior-based calibrations to induce node ages through biogeography, how can we actually condition on the biogeographic patterns we observed at the tip of the tree? So this is using a likelihood-based method that's very similar to how tip dating operates. So we're not using priors, we're using likelihood. Here's a cartoon of basically how this will work. So let's assume you have two areas, A and B, and you have a biogeographic pattern at the tips of the tree, like I said. For a given topology, the event is going to have to occur before or after these areas split, as you can see on the left-hand side. Now, if you treat the divergence times themselves as parameters that you wish to estimate, there's two possibilities. Either the event will occur after the divergence, after the area split, when the event is rare and you would assume that the probability is relatively low, or before, when it would be higher. Now you can also do this. The same logic applies if you're looking at how areas may merge over time. In this case, I have to add a fourth taxon, but it's the same principle. For the given biogeographic pattern on the right-hand side in the topology, if the areas have not yet merged, then you expect the probability to be relatively low of that history, and higher after that split event, or after that merge event, pardon. Okay, how can we formalize this a little bit? Well, to do that, what I'm going to do is I will evaluate the probability of change for a given branch length, where I'm varying the branch length with respect to age. So on the left-hand side, I have a tree, and I'm just computing the probability of some change occurring for that branch highlighted in blue, if it came out. Yeah, the branch highlighted in blue. And you can see for a constant model, and this is what we use for molecular substitution, the probabilities remain constant regardless of the age of the branch. You can see here, this is how the transition probability matrix is computed. And when you compute this, this doesn't admit anything about the age of the process when it's operating, which means the probability is constant, like I just showed you. Now, in contrast, let's say that you impose that structure, that paleogeographic structure I just mentioned. Well, as the branch passes over these intervals, called epochs in this case, the transition probability profile on the right-hand side, you expect it to respond to that structure. And that's what we see. The way that this is codified in the model, though, is for each time interval, now we have a different rate matrix. And that's going to give us the structure and the transition probabilities that we saw in that animation just a moment ago. So here are two possible paleogeographic structures, and you can just plot those right into the rate matrices. And this is a well-described operation. There's some challenges that arise, though. First of all, what's a good paleogeographic structure? Well, I think like many biogeographers, I've always been very fond of continental drift. It's a very well-described process where we have reasonably good estimates for when these events occur. This was laborious for me. I don't have a strong background in paleogeography. To perform this, I performed a literature review and used a tool called G-plates, which constructs these animations. There's one issue, which is how do you define what connectivity is? Here I'm interested in biogeography in terms of terrestrial connectivity. How might you define that? For this, I classified adjacencies between areas into 3 categories. 1, where there's strong connectivity, meaning they absolutely share land. 2 is a weak connectivity, and you can think of this as a rough measurement of how far is it to get from mainland Africa to Madagascar in modern day terms. And then the 3rd category is sort of a noise component, which is just implying that all of the areas are fully connected, and this is to approximate long distance dispersal. Now, the second issue that pops up is which of those 3 graphs should you use? None of them are really a good general description, are they? For this, I assumed that I had 3 components that for which I could weight, and treat that parameter, that weight parameter, as something to estimate from the data itself. So I don't have to make extremely strong assumptions about which graph I'm selecting. That's a parameter that's free in the model. So let's say I drew 1 part from each of these 3 components. You'll get something like this, the black line, and you can see it looks like an average between the 3. As I increase the importance of strong connectivity in the model, I get something that looks more and more like that pure strong component, right? So these are the types of probability profiles that the model is going to be trying to fit in the back end, which I'm not exactly showing you. But the second thing to keep in mind is that the probabilities and how they change over time will depend on the pair of areas that you're looking at. So here I have 2 scenarios. One is, say, South America to North America. That's what I've been showing you the whole time, by the way. On the bottom is from South America to Africa with respect to age. And you can see that these probability profiles, they recover some of the well-known events that are known to many paleontologists, biogeographers, and so forth. For example, on the top we have the formation of Pangea, and it's split later on, and a small tail at the end when the Isthmus of Panama forms. On the bottom, we have the splitting of West Gondwana. So it's nice that we have these intuitions, but how can we go about testing them? For this, I performed 2 types of experiments. First, I did a simulation experiment. You want to do a simulation experiment to say that you have some hope of actually inferring the parameters correctly in the real world. And then second, I used the crown group of turtles as an empirical experiment. And here's how it worked. For the simulation experiment, I simulated 50 data sets under the assumption that geography is important. Then I constructed the model so the prior distribution on the root age is flat. This means that if I ignore geography when I'm performing the model, when I'm performing the inference, I expect my posterior distribution to look like the prior distribution on the root age, because there's no information in these constant rate models. Now, if I condition on geography, I expect the posterior and prior distributions to differ. So here's how the simulations look. The top row is going to be when I ignore geography, and the bottom row is when I condition on it. The lines are the credible intervals, and the dots are the posterior modes for these parameter estimates. The red line is the true parameter that I'm hoping to target, and when the black line, or the black dots, match up with the red line, I'm doing pretty well. In general, you can see that when I condition on geography, I get a much closer match between the black and red lines, and much narrower confidence intervals. This is both for the root age estimate and also for a statistic that I'm not describing in detail. Essentially, you want this to be 0 when your estimated tree perfectly matches the simulated tree. So this is promising. This means if we perform an empirical analysis, we might be able to get some good parameter estimates out of it. For this, like I mentioned, I used the crown group of turtles. There are a handful of reasons to use this system. First of all, they're very well studied. Second of all, they have a really great fossil record, which means that there's good estimates for when different clades originated. Third of all, I would describe them biogeographically as slow and steady. They don't have a very erratic pattern where they're jumping back and forth between continents every 100 million years. That's a very long time. Every 10 million years. and moreover, they're old and widespread. And for this paleogeographic model, that means they're right in the ballpark of the types of dates that I want to estimate. They also have this classic Gondwanan ancestral distribution in the southern hemisphere, where they later disperse into the northern hemisphere, just before the breakup of Pangea. Now, the system's particularly nice because with their fossil record, there have been numerous estimates for the root age of the group, only using fossils. So what I can do is I can try to estimate the date using only biogeography without any fossil evidence and see if I can get consistent estimates with what's reported in the fossil-based literature. Now the model's set up in the same way where I expect that when I ignore geography, I have the same root age distribution. When I condition on it, I hope to see a peak. So here is when I ignore geography, I get that flat root age distribution. That shouldn't be too surprising. When I condition on geography, I get a peak around 200 million years. I can also, so the biogeographic dating methods that I've been discussing are also compatible with fossil-based dating methods, which means I can apply other fossil-based information and not introduce any type of inconsistency in the assumptions of the model. So here I've applied a root age calibration, and essentially what you'll see is it truncates the posterior distribution if I ignore that calibration. So, but in either case, whether I include or exclude fossils, I get approximately the same mode for the age. The last piece is I said I can compare this to the fossil-based literature. By my eye, I get a fairly good overlap. Here are 9 studies using a variety of methods, including parsimony, rate smoothing, prior-based methods. All of these are falling right around the peak of the estimate that I get, assuming using a biogeographic dating approach. Now this is nice for 2 reasons. First, it means that if I have no fossil data, there's some hope of retrieving the true root age using biogeographic method. Secondly, these fossil-based estimates could be further improved by incorporating biogeographic data. These are not final estimates, and you see they have quite a spread themselves. The last thing that I'd like to mention is that I am doing joint inference over molecular and biogeographic evolution. So a natural byproduct of this is I get ancestral state estimates over the tree. These are incorporating the phylogenetic uncertainty of the tree itself. So it's not as though you have to choose using biogeographic events as priors, and then you cannot use them in subsequent analyses for biogeographic reconstructions. You can do it all in one go. That more or less concludes what I'd like to share with you guys today. The basic points are that, in principle, and I feel I've shown, is that paleogeography should inform the biogeographic process. The biogeography should have some influence on the speciation times, and that you can learn the importance of the geographical constraints from the data itself. I have a recent manuscript up now in systematic biology, and I have some resources there for you if you want to dig into the details of the method. Okay, that's about it. I have some people to thank, and I think I'll just take questions.